Energy can be stored in batteries for when it is needed. The battery energy storage system definition is an advanced technological solution that allows energy storage in multiple ways for later use. Given the possibility that an energy supply can experience fluctuations due to weather, blackouts, or for geopolitical reasons, battery systems are vital for utilities, businesses, and homes to achieve a continual power flow. A battery energy storage system BESS is no longer an afterthought or an add-on, but rather an important pillar of any energy strategy. The advantages of battery storage systems are many. They make renewable energy more reliable and thus more viable. The supply of solar and wind power can fluctuate, so battery storage systems are crucial to smoothing out this flow to provide a continuous power supply of energy when it's needed around the clock, no matter whether the wind is blowing or the sun is shining. Plus, they can protect any user from grid fluctuations that could compromise energy supply. Here are some of the advantages of battery storage. Environmental gains. Installing a battery storage system in a home or business powered by renewable energy reduces pollution, thereby contributing to the energy transition and combating the effects of global warming. Lower energy costs. Storing low-cost energy and consuming it during peak periods when electricity rates are higher allows a user to shift consumption and avoid higher charges, saving money. The savings are magnified when combined with solar power, which is free. Less dependent on the grid. Battery storage systems guarantee a continuous energy supply, even at times when the energy grid is unstable due to peaks in demand or extreme weather. Always-on supply. The sun is not always on. A battery storage system works round the clock, and therefore compensates for any fluctuations in solar energy supply by storing any excess power in the system. Resilience. A battery storage system provides emergency backup in the event of a power outage, guaranteeing business continuity. Battery storage technologies are essential to speeding up the replacement of fossil fuels with renewable energy. Battery storage systems will play an increasingly pivotal role between green energy supplies and responding to electricity demands. Battery storage, or battery energy storage systems BESS, are devices that enable energy from renewables, like solar and wind, to be stored and then released when the power is needed most. Lithium-ion batteries, which are used in mobile phones and electric cars, are currently the dominant storage technology for large-scale plants to help electricity grids ensure a reliable supply of renewable energy. The term MNZT, minimum non-zero time, in the context of battery energy storage refer to the shortest time period in which a battery can store energy before it starts to discharge or lose its stored energy. This time period can vary greatly depending on the type of battery, its capacity, the load it's supplying, and other factors. The importance of energy storage, particularly in batteries, is immense in the context of renewable energy and the transition to a climate-neutral economy. Batteries play a crucial role in the rollout of zero-emission mobility and the storage of intermittent renewable energy. They are instrumental in helping power the rising digital economy and an ever-growing number of portable electronics. As for the way forward, the future of energy storage is promising but also challenging. The global demand for batteries is increasing, driven largely by the imperative to reduce climate change through electrification of mobility and the broader energy transition. The entire lithium-ion battery chain, from mining through recycling, could grow by over 30% annually from 2022 to 2030, when it would reach a value of more than $400 billion and a market size of 4.7 TWh. Many challenges lie ahead. To avoid shortages, battery manufacturers must secure a steady supply of both raw material and equipment. They must also channel their investment to the right areas and execute large-scale industrialization efficiently. And rather than just greenwashing, making half-hearted efforts to appear environmentally friendly, companies must commit to extensive decarbonization and true sustainability. You can see the classification of energy storage technologies, which is divided into mechanical, electrochemical, thermal, electrical, hydrogen-based storage. Further detail one can see in this table. Research is focusing on finding a solid or semi-solid electrolyte that can prevent dendrite growth whilst also facilitating the easy passage of lithium ions. Current predictions estimate that solid-state batteries with twice the capacity and faster recharging will be on the market by 2025. Intelligent battery software uses algorithms to coordinate energy production, and computerized control systems are used to decide when to store energy or to release it to the grid. Energy is released from the battery storage system during times of peak demand, keeping costs down and electricity flowing. Path forward is challenging. The potential benefits of advancing battery technology and energy storage are enormous, both for the environment and for the economy. The key will be to navigate these challenges strategically and sustainably. BESS and network system services. Voltage control services. BESS can be used to provide locational ancillary services. Like, for example, voltage may drop at the end of long power lines in a dispersed network, which can lead to increased faults and outages. Voltage can fluctuate more as supply-side volatility increases with higher VRE penetrations. This type of service requires the BESS to be located at a site where the voltage support will be effective. Another example of a locational system service would be using the BESS to improve system reliability in a specific locality, for example, covering an economically important industrial park. This could provide a useful way of addressing the concerns of investors in industrial or manufacturing facilities, without having to address all the complex and interrelated challenges of the electricity system simultaneously. BESS and frequency control services. The provision of other ancillary services is less dependent on location. Like, for example, reserve services or frequency response could potentially be provided anywhere on the system, subject to connection constraints. BESS can respond much more quickly than many other flexibility providers, providing a response in less than 1 second. As VRE increases, this results in declining system inertia, which in turn results in a higher rate of change of frequency roll-off. Higher roll-off increases the demand for very fast frequency response services. The graph illustrates how BESS can be used to restore system stability. System frequency typically needs to be maintained within a fixed band, typically 50 Hz plus or minus 0.5 Hz. If a large generation outage or a sudden drop in outputs from VRE results in a fall in system frequency, the BESS can respond very quickly to restore stability. Battery C rate. Charging and discharging of BESS. A battery C rating is the rate at which a battery can be fully charged or discharged. For example, charging at a C rate of 1 C means that the battery is charged from 0 to 100% or discharged from 100 to 0% in 1 hour. A C rate higher than 1 C means a faster charge or discharge. For example, a 2 C rate is twice as fast, 30 minutes to full charge or discharge. Likewise, a lower C rate means a slower charge or discharge. As an example, a C rate of 0.25 would mean a 4-hour charge or discharge. The formula is T equals time. CR equals C rate. T equals 1/CR to view in hours. Or T equals 60 minutes/CR to view in minutes. See the table for example. Question is: what renewable energy storage systems are being developed? Storage of renewable energy requires low-cost technologies that have long lives. Charging and discharging thousands of times are safe and can store enough energy cost-effectively to match demand. Lithium-ion batteries were developed by a British scientist in the 1970s and were first used commercially by Sony in 1991 for the company's handheld video recorder. While they're currently the most economically viable energy storage solution, there are a number of other technologies for battery storage currently being developed. These include compressed air energy storage. With these systems, generally located in large chambers, surplus power is used to compress air and then store it. When energy is needed, the compressed air is released and passes through an air turbine to generate electricity. Mechanical gravity energy storage. One example of this type of system is when energy is used to lift concrete blocks up a tower. When the energy is needed, the concrete blocks are lowered back down, generating electricity using the pull of gravity. Flow batteries. In these batteries, which are essentially rechargeable fuel cells, chemical energy is provided by two chemical components dissolved in liquids contained within the system and separated by a membrane. Now I'll talk about store, which is short-term operating reserve. Battery storage systems play a crucial role in the energy sector, particularly as a short-term operating reserve store. Store is a service that provides additional active power from generation or demand reduction. In the context of battery storage, it refers to the ability of a battery storage system to store energy when demand is low and then release it when demand is high. This helps balance the grid, ensuring that supply always meets demand. Battery storage systems are particularly useful for integrating renewable energy sources like solar and wind into the grid. These sources are intermittent, meaning they don't always produce power when it's needed. For example, solar panels don't produce power at night. Battery storage systems can store excess power produced during peak production times and then release it during times of high demand. The minimum non-zero time challenge is closely related to the life of the battery storage systems. There is a strong connection between the short-term operation and life of the battery storage systems. This means that the decisions made for short-term operations have long-term consequences for the life of the battery technologies. Addressing this challenge requires advances in battery technology, including the development of new materials and systems. Research focusing on finding a solid or semi-solid electrolyte that can prevent dendrite growth whilst also facilitating the easy passage of lithium ions. When we talk about BESS, California is the best example. California, a world leader in energy storage with the largest fleet of batteries that store energy for the electricity grid. Energy storage is an important tool to support grid reliability and complement the state's abundant renewable energy resources. These technologies capture energy generated during non-peak times to be dispatched at the end of the day and into the evening as the sun sets and solar resources go offline, reducing dependence on fossil fuel generation to meet peak loads. Here one can see the detail about California energy system showing 6,617 megawatts of capacity, where residential capacity showing 843 megawatts. Commercial capacity is 540 megawatts, while utility capacity is 5,234 megawatts. So total stands 6,617 megawatts. In this table one can see 100% clean electricity by 2045 by California. Latgets portion under plan is utility solar PV. Then battery and wind. Geothermal, long-duration energy storage offshore wind also under plan. Battery storage system main applications. Battery storage can be used in many ways that go beyond the simple emergency backup in the event of an energy shortage or blackout. Applications differ depending on whether the storage is being used for a business or a home. For commercial and industrial users, there are several applications like peak shaving, or the ability to manage energy demand to avoid a sudden short-term spike in consumption. Load shifting, which allows businesses to shift their energy consumption from one time period to another, by tapping the battery when energy costs more. Flexibility, whereby customers can reduce their site's grid demand at critical times without changing their electricity consumption. Energy storage therefore makes it a lot easier to participate in a demand response program and save on energy costs. Microgrids rely on batteries as a key component, because these grids need energy storage to enable them to disconnect from the main electricity grid when needed. Integration with renewable energy sources, since batteries guarantee a smooth and continuous electricity flow in the absence of the availability of power from renewable. Residential users benefit from application of energy storage system by self-consumption, since residential users can produce solar energy during the daylight hours and then run their appliances at home at night. Emergency backup in the event of a blackout. Going off the grid, or detaching completely from an electrical or energy utility. One can see here services offered by utilities batteries, where important aspect is system operation of BESS, solar PV and wind generator. And lastly mini grid offered by BESS.